We are on, should be what, lesson 9? Dang, we're almost a quarter way through the semester. How'd that happen? Okay. So we are, from an admin standpoint, just as a reminder, I actually get to have you 3 times this week, which is rare between our weekends and everything. So we're going to be meeting 3 times this week. Wednesday, big thing is you guys got homework 6 and 8 due there, as well as lab 3. And I came in this morning and it looks like I got a bunch of messages from the weekend. So as soon as I'm out of this class, I will start burning through those, either answering your questions, or if you're looking to schedule EI today or tomorrow, I am at your disposal. We'll make it work. I will schedule those in the order that I got them. Quiz 2 opens on Wednesday, same rules as before. It will open Wednesday morning, and you have from Wednesday morning until Thursday evening to take that. I think most people were able to do it last time. If you were one of the people who had technical problems, then make sure if that was sorted or not that you let me know. That should not be the thing stopping you from taking it. As a reminder, I said this last time, I'll say it again. If you are a ESL student, and if you want extra time on the exam, you are have that as a right. So just send me a direct message, and I can update that in Blackboard so that you get the extra time if you think you need it. I think those are my main questions. Anyone have a question besides Shane? Do you have a question, or are you just rubbing your mic all over your body for fun? Shane? You got anything, Shane? No? All right. Yeah, okay. Shane's done. All right. Anyone else got any questions or need to get some mic rubbing out of their system before we start?
I got a quick question on the lab on whenever it asks, like, whenever they're above the average. So for that, would you take the ones that contained Michael, subtract it from the ones that are above average, and then divide by Michael?
You got to give me a little bit more specific. I'm trying to remember. I don't have the entire lab memorized. So you're saying, how would you compare?
Yeah, so the question asks, like, what is the probability that a rating is above average given that the description contains Michael?
Right. Okay. So what I always suggest for this type of thing is to say something like, so you says the probability that it is above average, given that it contains Michael?
Yes, sir.
So you're saying probability that it's, I'm just going to say above average, given that it includes Michael, right? And then, so that's the mathematical thing you're asking, which mathematically, what you're saying is, what is the probability that it is a above average and includes Michael, divided by the probability that it includes Michael, right? That's the, if I could write correctly, that is the definition of conditional probability. And so once you have that, then you could just say, all right, well, I'm going to count how many times this happens. So just do code that says how many episodes are above average and include Michael, and that will be some number. And then count how many have Michael, that'd be some number, and then that's your probability, right?
Okay, so how would you get R to go in and find all values that were above average that contained Michael? Because I've found all values that contain Michael for a description and all.
So I'll give you two things on that. One, if you didn't see it on the weekend, I had 2 people actually ask me a similar question. So on the YouTube channel, and if you want, I can send you the link, but it's one of the most recent ones. I did a short video on how to do logical expressions, like how to do ands, ifs, things like that, to say, how do I go through and tell me all the things? And the main, but I'll tell you the main gist of that is, if you don't already know, when you search logical expressions, true, falses, R counts a true as a 1 and a false as a 0. So if I said, and I'm going to use very vague kind of general code here, if I were to tell R to say, if I wanted above average and Michael, if I said, let's say I'd already found the average and I called it the variable AVG, right, average, then if I said what I want is office $, rating is above AVG, so that's going to be say, hey, when rating is above average, and then I'm going to use ampersand and then you know, off the top of my head, I'm not going to just, you know, grapple or and then I say, you know, how do I say this? I would say if you let's say you made a
if you were to
another
put that as a variable, can you just say average and Michael?
Right. So yeah, if you made a variable has Michael that's true or false, you could say this and then say and office $ has Michael, right? So that would be an and. So that's going to return true every time both of those are true and false every time it's false. And then if you wrap that all in parentheses and say sum, then what it'll do is every time there's a sum, that count true is a 1 and false is a 0. So that will count how many times that and statement is true.
Okay.
Does that get you in the right direction?
Yes, sir. Thank you.
Yeah, and if you get stuck, just shoot me a message. That's the type of thing that we could probably iron out within some messages. But then if you need to, we could follow up with chat. Okay.
All right. Thanks, sir.
Cool. Definitely. That is what I like to do. Answer questions. Okay. So today we are going to talk about normal random variables. And 2 lessons ago really was the last time for this block that we introduced anything truly new. Everything else from then on is what I like to say is same but different, right? So we introduced random variables 2 lessons ago on lesson 7. Then in lesson 8, we said, hey, remember random variables? Now we're going to talk about a specific kind of random variables, continuous random variables, right? So we showed, hey, here's what a continuous is. It's the same, but instead of sums, we do integrals and all of this, right? So it was new, but not different. Same thing today. Today, we're going to say, hey, remember continuous random variables? Let's talk about a very specific kind of continuous random variable, the normal, right? And that's what we're going to do for the rest of the block. After today, then we're going to talk about specific kinds of discrete random variables. So they still follow the general random variables rules, but they have specific things about them. And because they are a name distribution that comes up so much, they have their own functions in R, so we can start to calculate things instead of having to do it like we've been doing up to this point where we just directly count things, right? Now we're talking about distribution. It's kind of like rolling a dice, right? Rolling a dice is a discrete, but it is a specific distribution where there's 6 options and each one has a probability of 1/6. It's specific and we know all the rules for it, but you don't use it that much unless you work at a casino or you play a lot of games, right? The normal distribution is like that for continuous. It is a name distribution that has its own rules that we can exploit, but unlike the dice, it comes up way more often and it has better rules. So, and we have functions in R for it. So that's what we're going to do today. It still is a random variable. It still is a continuous random variable and follows all those rules we had, and it has a expected value and a variance just like before. It's just now we have some additional rules about it that we can exploit to make our life easier. So the normal distribution looks like this. It always looks more or less the same. This is the probability density function. It's always basically the same shape. It's this bell curve, right? Anytime, even though if you haven't used it directly, you've probably heard of it or seen it. Anytime you've heard normal distribution or Gaussian distribution or the bell curve, or just anytime you've asked a professor if they were going to curve your grade, whether or not you knew about it, you were talking about the normal distribution. And not surprisingly, it's called the normal distribution because it is very normal in nature and science and everything. It comes up all of the time. It is literally a distribution we're going to be using for the rest of the semester, right? And the nice thing about it is it has some properties that no matter what how we change it, there's different instances of it. It always has the same basic shape, and it always is symmetric, right? It is exactly symmetric around its mean, right? And it is the normal distribution. While I can have different normal distributions, any normal distribution is uniquely defined by two characteristics. Its mean, or mu, and its sigma, or standard deviation. If you guys remember, sigma, or the standard deviation, that is the square root of variance. So it is a measure of how spread out the probability distribution. So notation wise, when we write something like that, what we are saying is the random variable x is distributed normally with a mean of mu and a standard deviation of sigma, right? So the mean tells me where it's centered around, and the sigma tells me how spread out it is, right? So I can have a normal distribution like that, or I could change the mu and it would shift to be centered around 20, and I could make the sigma smaller, which is going to make it thinner, which is going to make it taller, right? Because this is still a probability density function, and so the probability is the area under the curve. So the area under the curve still has to always add up to 1. So if I make it spread out less by making sigma smaller, then the height has to go up as well. And remember, this is a probability density function because normal random variables are continuous. So probability, we can only find probability for ranges underneath the curve, and the height of the function doesn't mean probability. That just is the density. That's how tightly packed the probability is. So any questions on basically the general shape and how it is defined by these two characteristics, the mean and the standard deviation? Okay. Next thing I want to talk about is this concept of a z-score, which sounds complicated, but really is not, right? So what the z-score is it is a score I can calculate for any specific value of the random variable. So in this case, I have a random variable x. I could say, hey, one possible value for this random variable is 22. And I could calculate the z-score for 22 and say the z-score for 22 is 22 minus the mean, which in this case is 20, divided by the standard deviation, which in this case is 1.2, which equals 2 divided by 1.2, which equals about, I think, 1.6 repeating, right? So that is my z-score, right? And so what that is, if you look at it, is just how many standard deviations away from the mean I am, right? Because that numerator, x minus mu, that's just finding how far away my particular number is from the mean. Then I take that and divide it by the standard deviation to tell me how many standard deviations that distance is, right? So that's all the z-score is. The z-score is just a measure of how many standard deviations away my particular x value is. If I was to the left, it would be negative, so it also tells me if I'm on the left and the right, but it's how many standard deviations away that I am. And we're going to get more into the specifics of this later, but the reason that is useful is because it gives me a way to compare different normal distributions, right? Because I said I can have a different mean or a different sigma for different things. But I'm going to make up a situation. So my numbers are going to be, my actual distributions are going to be wrong, but the concept is the same, right? So let's say that the height of a person is distributed normally with a mean of 70 and a standard deviation of 2. That's, I'm sure, not right, but let's say it's about that, right? So that's saying that the expected value of a height is 70 inches and that the standard deviation is 2, right? Now let's say that I have another normal random variable s that is also distributed normally, but we're going to call that shoe size. So let's say, I don't know, let's guess that the average shoe size is 9 and that it has a standard deviation of 5, right? So these are both normal distributions, but they are very different, right? One is centered at 70, one is centered at 9. one is spread out based on a standard deviation of 2, one is spread out with a standard deviation of 0.5. And they're different units, right? Height is in inches, shoe size is in, I don't know, shoe size, I guess is just the units for that. So I can't compare them directly. I can't say what's bigger, his height or his shoe size. I mean, I could, but that's a dumb statement. But what I really even couldn't do that because I'm not comparing inches to inches. But what I could do is I could say, hey, one person, I met two people. One had was 80 inches tall, and the other person had a shoe size of 13. And I could ask the question, what is more unlikely? Is it more unlikely to find someone who is 80 inches tall, or is it more unlikely to find someone who has a shoe size of 13? And this is where the z-score comes in handy, because I can calculate the z-score of both of these, and I can say, all right, for 80, the z-score for 80 is, I'm talking about height, so 80 minus mu, which is 70, divided by sigma is 2. That's 10 divided by 2 is 5. And then for a shoe size of 13, that's 13 minus mu for that one, which is 9, divided by standard deviation for that one, which is 0.5. So 13 minus 9 is 4, divided by 0.5 is 8, right? And so now I can actually compare these, because a shoe size of 13 is 8 standard deviations away from the mean, right? That's what the z-score means. It means it is that shoe size of 13 is 8 standard deviations away from the expected shoe size, right? Whereas the height got a z-score of 5, which means it is only 5 standard deviations away from the expected height of 70. And so therefore it is more unlikely that I would get a shoe size of 13 than it would be that I would see someone with a height of 80, because standard deviation, because now I'm comparing them using their own metrics, right? I'm not saying I'm 5 away or 10 away. What I'm saying is, here's how many standard deviations how many of the distribution standard deviations I am away from its average, right? So I'm now comparing apples to apples. And so I can say that it is more likely to find someone who is 80 inches tall than it is to find someone who is 13, has a size 13 foot. That is the main reason and the power of the z-score, is to be able to compare two different normal random variables in likelihood and probability. Any questions on what I did there or what that means and how that could be useful? The other side reason of why that was helpful is back in the day before I had R or anything like that, if I wanted to find the probability of something, I couldn't just type into R and say, what's the probability? I had to look into a table that someone had meticulously made with a computer bigger than my room, right? But they couldn't have a table for every probability, because they couldn't say, here's a table for heights, here's the table for shoe sizes, here's a table for the beak length of an ibis, right? And so what they would do is they would just say, hey, we're going to give you just one table, and it's going to be of the standard normal. So a standard normal is basically a normal distribution where everything is a z-score, right? Because here standard deviation is 1. So when I count standard deviations, it is the number. And so I would look it up in there. I would say, here's my distribution. I'm going to standardize it by finding the z-score, and then I will look it up in the standard normal, right? Because the standard normal, everything is already there. I can't do a z-score, right? If I say, if this is my normal distribution where the mean is 0 and the standard deviation is 1, and I go, hey, what's the z-score for 3.3? Well, it's 3.3 minus the mean divided by the standard deviation. Oh, that's just 3.3, right? And so the standard normal is where everything has already been z-scored. And so we work in that a lot of time, because that is basically the distribution where everything, the x's are all of the z-scores, okay? Any questions on what a standard normal distribution is, right? It's this one where it is centered around 0 and the standard deviation is equal to exactly 1. So it is a distribution where everything is a z-score already. Okay. The other nice thing about the normal distribution, we've already said that it has the nice rule of being symmetric and only being, only need to know the mean and the standard deviation to define it. One of the other really nice rules it follows is this rule called the 68, 95, 99.97 rule, right? And all that is saying is, give me any normal distribution. In this case, I've got the standard normal. And so the probability of being between one standard deviation below the mean and one standard deviation above the mean is about exactly 68%, right? In this case, I just said between negative sigma and positive sigma because I'm in a standard normal and I'm centered around 0. If I'd had something like our height normal random variable like this, then I would say there's a 68% probability that the height is between, that a random height is between 68 and 72 inches because I'm centered at 70 and one sigma on either side of that would be from 68 to 72. And so there is a 68% probability I'm within that range, right? And the rest of the rule goes just follows the same idea. If I go 2 sigmas away from the mean, there's a 95% probability that I am within 2 sigmas of the mean. And if I go without 3 sigmas, there's a 99.97% chance that I am within, and I just realized my numbers are wrong up here. I should have an extra 9 in there. But there's about a 99%, almost every probability of being within 3 sigmas, right? And so the normal distribution goes on to negative infinity and positive infinity in each direction. However, this is the important idea that there's a 99.97% probability that you're within 3 sigmas. You know, same thing for the height. Is it possible that someone is 95 inches? Yes. Is it likely? No, because 99.97% of the time we're expecting to be within 3 sigmas of the mean. That's all the rule is, right? In fact, if you've ever been in a business or a management class and you've ever heard the term 6 sigma, the term 6 sigma comes from here because it's basically saying, hey, I want to try to predict all of the probable or possible problems we could have. And it's acknowledging that if I could be within 6 sigmas of my expectation, right, 3 sigmas on either side, so this range of 6 sigmas, that I will be, that means I am anticipating 99.97% of all possible problems. And that's actually pretty darn good, right? So that's where the term 6 sigma comes from. It's talking about that range of a normal distribution that covers almost all probable situations that may arise. Questions about this rule? As a reminder, just as a side note, there are other things that knowing this rule helps you out on, right? Because if I know that this is, I'm just using an old drawing here, that 68% is in a range here. In fact, I can just use a new form. If I have some normal distribution and here's my mean, and I know that 68% is in here, I also know that it's symmetric. So I know that right here that this is 34%, right? So I know that the probability of being less than the mean, but within sigma is 34% because of that symmetric nature. Just something to think of as we go through here is remember that you know some basic probability rules along with the rules of normal. You can figure other stuff out. Okay, now we're going to get to the good stuff. We're going to say, these are all the things that we went through already that I need you to understand conceptually about the normal distribution, about what it looks like, how it's symmetric, how the mean and the sigma are the only things you need to tell me the specifics of it, that the area underneath it is always 1, how to calculate a z-score, and what the standard normal. But at the base, those are almost all like conceptual ideas. If we get to the point of saying, now I want to find the actual probability of something, well, that's where R comes in. This is where I'm really hoping that R starts to be your friend instead of something that you hate, right? This is where it should be helping you. I'm going to start giving you the equations of doing R. And remember, This is open everything class. So you do not need to memorize these functions. You just need to write them down somewhere. You can write them on paper, or you could open up an RMD file and just save it and comment it copiously for yourself. You don't even have to do that if you don't want to. After we're done here, I'm going to open up an example R program to show you how to use these functions. But I save that R file in my instructor folder, the same place I do my slides. So you can download that, keep it, add comments to make it make sense to yourself, or make it, cut, paste out, whatever you want, but put it somewhere so that you know how to use it. All right, so we're going to go over 4 main functions that you need to be able to use for doing stuff with a normal distribution. First one is denorm, okay? Denorm, think of it as density. I have three arguments that this needs, this, and this. There are more arguments that you could give it, but I don't want to keep this complicated. So these are the basic ones you need. And so I need to always give it, in this case, the mean and the standard deviation, because R needs to know which normal distribution you're dealing with. And like we said before, it's defined by mu and standard deviation. So as long as you give it those 2 numbers, it goes, okay, now I know everything about the distribution. What do you want to know about it? And so the first thing I can say is denorm. And so denorm is the density. So when I put in 0.5, what I'm saying is for x equals 0.5, what is the height of the function, right? Which, remember, for a probability density function, the height of the function is not the probability. It is just it's the density. It's how tightly packed it is. It's how high the function is, right? So denorm gives us an interesting number, but to be completely honest, it's not a number we use that much in real life. It's important you know what denorm does, but for a normal distribution, it's just the height of the function, which is not a probability, so it's not something we use as much. Questions about denorm? All right. The next one is going to be your money function. Next one is P norm. P for probability, right? And so I still have to give it, hey, here's the particular normal distribution I'm talking about. But now I am saying, when I give it 0.5, what I'm saying is for x equals 0.5, what is the probability of being less than 0.5, right? So when I write this function, what I'm really asking is, what is the probability that x is less than or equal to 0.5? And it's going to find it for me and say, oh, it's 0.691. That's what p-norm means. Now, side question, this is kind of a concept question. If you were following everything else before and you've got it all straight in your head, I should be able to ask you, you don't need R to do this. If I said p-norm, and then I said, instead of 0.5, I just said 0. And then I said mean equals 0 and standard deviation equals 1, like I did before. Anyone have any idea, got a guess of what number R would spit back for that? I could put it in R and calculate it, but based on what we've talked about before, you guys should be able to figure that out. Yeah, Shane, what do you got?
0.5.
0.5. You scared me when you started 0, and I was like, oh no, but then you said 0.5. I was like, yeah, I pulled it in at the end. Yeah, it'd be 0.5, right? Because this is a mean of 0. So I'm asking, what is the probability of getting a value less than 0? And since the normal distribution is perfectly symmetric around the mean, it better be exactly half, right? So I'm not saying you have to calculate that on your own, but that is the type of thing that you can use for common sense, right? Because in this case, you could say, well, I know the probability of being less than 0 is 0.5. I'm asking of being a probability of a little bit bigger than that. And so I'm expecting a number a little bit bigger than 0.5. Yeah, 0.691, that could be right, right? That's the kind of common sense I want you guys to cultivate and do on your, when you're doing your tests and labs and things like that, because I've actually already seen this a couple of times in labs. And I should tell you guys, like, I always want you to get perfects on your labs. And if you have a really stuck on something, I hope that you guys have the time to text me and we set up a meeting and talk. But in the case that you're not, if there's a question of saying, blah, 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 what is the probability of this happening? If you say, and the probability is 1.3, if you say the probability is 1.3, comma, but I know that can't be right because probabilities can't be greater than 1. I messed up somewhere in my code. I just don't have time to fix it. I'm sorry. I'm going to give you 1 to 2 points more than the person who said the probability is 1.2. Done. Drop the mic. I'm not even going to say anything because either that person completely doesn't understand probability, or they do and they just don't have the time to do it, and they're hoping that they can BS and get away with me. I don't think that's any of you guys, but acknowledging that something can't be right. Best case scenario, if you have more time to work on it, you go, okay, that can't be right. Let me go back and look at it. Worst case, at least tell me that it can't be right, right? And so here, the common sense should tell you, yeah, that sounds reasonable. If you got something that was less than 5, I would hope you would say, oh, that can't be reasonable because I was expecting it should be greater than 0.5. What did I do wrong here? John, what do you got?
So P norm is just taking the integral from the very start of the bell curve to whatever point we give it.
Yep, exactly. And a good point that he said here is he said integrating from the very start. So this is why it's nice to use R, because technically speaking, if you had to do this integral, it goes on forever to the left. So if you were actually doing the math, it would be the integral from negative infinity to 0.5 of the normal equation, which I didn't even show you because it's annoyingly big. And I've seen other instructors who put it on, and if they're putting it on in a math majors class, that's fine. They need to know what it is. If I put it on here, I'd only be putting it on to show you how big and scary it is so that you would say thank you for letting you use R. But I'm not even going to do that. You don't need to see it. It's in the book if you want to see it. It's big, long, and scary. But yes, it's finding the area under the normal curve from negative infinity to 0.5. Does that answer your question, or did I miss it?
I got it, sir. Thank you.
Awesome. Okay, next one is Q norm. Okay, this is where people get confused. It's really not hard, but I think people get confused because P and Q look the same. They're just flipped around, and it's a very subtle difference, but here is the main difference. P is probability. Q is quantile, right? And so if you remember when we talked about quartiles, if I said, hey, when we looked at ratings, the first quartile was the number below which 25% of your data was, right? So a quartile is a number. Quantiles are like quartiles. There just can be anything instead of 25%. So P norm, I give it a probability and it spits back an X value. Q norm, I give it a probability and it spits back an X value, which you can tell that wasn't a probability because it was a negative number, right? That can't be a probability. And so when I do Q norm of 0.25 here, what I'm saying is, hey, I want, if there's a 0.25 probability here, what is the X value that gives me that 25? To put it another way, it's like saying probability of X being less than or equal to some specific value of X equals 0.25. What X makes this statement true? And that's what Q norm does. It gives me back what is the value of X that makes that true. So P norm, I give it an X value, it tells me the probability of being less than that X value. Q norm, I give it a probability and it tells me what X value would have that probability of being less than that X value. Okay, it's a little confusing. Any questions on that? Anyone need more explanation, better example, or are you tracking on how Q norm works? I'm still on all of these. Got to give it the mean and the standard deviation so it knows what I'm talking about. Yep, no one's talking to you, Siri. But that is the difference between P norm and Q norm. Any questions on that? Yeah, what do you got, Chris? Oh, I forget. I said Chris, but how do you pronounce your name?
Shares.
Cheers. Okay. Yeah, what do you got, Cheers?
So you say that Q norm gives you the X value, the Y value, and the P norm gives you the probability for the X value?
So D norm gives me the Y value. P norm, I give it the X and it gives me the probability. Q norm, I give it the probability and it gives me the X value. Does that answer your question or did I miss it?
Could you repeat again for P?
Sure. So P, you're talking about for P norm?
Yes, sir.
So P norm, I put in 0.5 here And what it does, and I'll go back up to where I had, it says, if for 0.5, what is the probability of being less than 0.5? So it's literally finding probability that x is less than or equal to 0.5. This right here is solving this, which is the same as finding the area under the curve to the left of the x value 0.5.
Yes, sir. Thank you.
Cool. All right. Go down to Q norm. The last one that I want to show you is R norm. R norm is different than all the other ones because whereas the other ones either give you the Y value or the probability or the X value, R norm spits back a bunch of numbers because what R norm is, R stands for random sample. So what this does is this simulates a random sample of however many samples I want. I said 20 here, right? And so if I were to do something like R norm, and I did it for our height thing where I said 70, say 20, and then I said 72, that's going to give me 20 samples from that distribution. So it's going to simulate saying if the average height of someone is 70 with a standard deviation of 2, then it's going to give me back 20 heights that would be examples of the heights I would get if I randomly sampled from the population, right? And so this down here is saying from this distribution, give me 20 random samples of X. And so I'm going to expect, based on the 68, 95, 99 rule, that about 68% of them should be between -1 and 1. About 95% should be between -2 and 2, and so on, right? Which you can see, yeah, most of them are between -1, -1 and 1. And then I only have one that is almost 3 away, right? And if I don't, it's possible that I could have one as big as 8, but not in a sample size as small as 20. If I did a sample size of 100,000, then I might see some really crazy outliers, but that's what that is. It is for generating a random sample, which again, we don't use as much. It's not going to give us a number, but it might show up in a lab of saying, hey, we're going to do a simulation and see how this works out. And that's where R norm comes in handy. Questions about what the purpose of R norm is and what it spits out. Okay, now, a little preview of things to come. We're going to have, as after, like I said, the rest of this block, we're going to talk about different distributions. We're going to talk about binomial, geometric, Poisson, things like that. Each one of those are a distribution, but they are slightly different. Whereas here, I can completely define a normal distribution by its mean and standard deviation. For some of those other ones, they might need other things to define it. That being said, every one of those functions, I'm going to say, hey, here's what it is. Here's the scenario you use it for. But then there's going to be the same 4 types of functions. There's going to be the D function, the P function, the Q function, and the R function, right? So like when we get to the binomial distribution, in R, you're going to have D binom, P binom, Q binom, and R binom. And even though their parameters are going to be a little different, they won't have necessarily the mean and standard deviation. Each one is going to do the same thing. D is going to give you the height of the function. P is going to give you a probability. Q is going to give you back an X value when you give it a probability. And R is going to give you a sample. So make sure you kind of generally understand what the 4 categories of functions are for the distribution. And then you need to know how to use it for each one. But again, you don't have to memorize it. This is open everything. Put it into an R file and comment it and just make sure you feel comfortable using it. So before we spend, we got about a little over 10 minutes to look at the actual R code that I posted up. Anyone have any general questions on anything we talked about on this screen? Okay, so let's take a look at this. So like I said, this is posted in my instructor folder along where I put my slides. If you want to see it, download it, use it. You're not going to hurt my feelings. So a couple things on here. One, this first chunk of code is you don't have to understand it or do anything with it. This is a function I made up. I say it's a function I made up. I stole the code from a lot of different people and put it together. But like I was telling the last section, my advisor told me if you copy from one person, it's plagiarism. But if you copy from more than 5 people, then it's called research. So I'm going to call this research. And so you don't need to understand what this is. If you're interested, talk to me and we can have a real fun conversation on R. But this is just a function that if I run it, nothing happens, but it loads the function. And now I can minimize that. And now I have a new function that doesn't exist in R that I've made up that lets me draw the picture. It's where it helps me visualize things. So you guys feel free to use it to help you visualize yourself. If you find it confusing, just delete it. You don't have to use it. So the first thing is this idea of dnorm, right? Which is the probability density. So if I run this, dnorm of 85, so I'm saying, what is dnorm of 85? But I'm changing my distribution. So I'm no longer standard normal. Now I've got one that is a mean of 100 and standard deviation of 15. So here's the picture of what it looks like, right? Dnorm is just the height at 85. I'm not calculating the probability, it's just the height. And so I can go over here and the console says, here is what it spit out, it's 0.016. It's not I can't say that's 1.6% because it's not a probability, it's just the height. That is the, dnorm is the height of the function of this, right? I can then go down to our next section and say, well, what if I wanted to find the probability that X is less than 85, right? Now, if you remember when I was talking to the screen, I said probability that X is less than or equal to 85, and here I'm saying less than, so I'm a little loose with it, but I'm actually allowed to do that with continuous random variables, because if you remember, continuous random variables, we talk about ranges. The probability of any one number is 0. It's different than discrete. Remember, I roll a dice, the probability of a 4 is 1/6. But with a continuous random variable, I have to talk about ranges. If I say the probability of exactly 85, that's 0. So I can actually say, when I talk about the range, I can say less than 85 or less than or equal to 85, and it doesn't change it in this case because exactly 85 is 0. So it's a little sloppy of me, but I'm mathematically allowed to do it. And like we saw, that is P norm of 85, mean of this, and the second part's just draw it. And I can see there is what it looks like. It is probably, it's about 16%, which I'm asking the probability of being less than 85. I know the mean is 100, and so I know that it better be less than 50, and I could do some other things to convince myself that that's a good answer, but it definitely does work out. Another thing, just as a side note, this came up earlier, I think it may have been Shane who was saying it, or maybe I think it was John, that when I'm finding probabilities, I say, hey, what's the probability of less than 85? To tell R, I had to tell it, what's the probability of it being between negative infinity and 85? Because it doesn't just do strictly less than. R actually has infinity as a number. So capital I and F is infinity in R. That's why it shows up when I write it there as red. If I were to here say capital I and then I put an F and it turns pink, it goes, oh, now that's a number, right? And so I can use capital I and F or negative I and F to do things that I am allowed to do infinity with. And so that's why that works there. Okay, I want to get into these next couple examples. So we talked about probability of being less than something. What if I want to be probability above it? So there are some additional parameters that you can put into P norm and things like that to tell it I want probability of greater than. If anyone wants to know those, let me know and I'll tell you. But I think it just complicates it to start putting in those things. I think it's easier in my mind to just say, to recognize that, well, the probability of it being greater than 85, that is the same as the probability of it being less than 85. If I really wanted to be clear, I could put in equal, so I'm covering all the options. But those are the same things, right? Because the total probability under the curve has to be 1. So the probability of being greater than 85 has to be 1 minus the probability of being less than 85, right? And so once I acknowledge that, then I can just use my same code I've been using before. I can just say 1 minus the probability of being less than 85. And I can run that code. And I get an answer of 0.84, which I can think about for a second, say, does that make sense? The mean is 100. I'm asking the probability of being greater than 85. So the probability of being greater than 100 would be 50. And so the probability of being greater, 50%. And so the probability of being greater than 85 should be bigger than that. So 84 seems reasonable. And if you use the little draw thing, you can see, yeah, that looks about right. And again, I get from 85 to infinity to see that range. Anyone have any questions on why I can use this equation at line 65 here, why that's mathematically true? I want to make sure that I don't gloss over that everyone feels comfortable with that substitution I did at line 69 to find a greater than probability. Awesome. Okay, so then what if instead of less than or greater than, what if I wanted to do a range, right? What if I said the probability that X is between 85 and 120, right? So this is, again, let's just think about it in terms of, if I say, hey, here is my my thing, and it's 100, and I say 85, well, it'd be great if I could write, to 120, right? And I always suggest drawing, if you don't have my little draw thing, make your own bad picture, right? This is obviously a bad picture, but it still gets me the idea to say, I want to find the probability between 85 and 120, which means I want to find that area and go, I don't have a function for that, but I can find the probability of being less than 120, which would be all of this, but that's too much because I don't want this part. Well, this part is the probability of being less than 85. So if I take the probability of being less than 120 and subtract off the probability of being less than 85, then what I'm left with is the part that I want. Does that process make sense? Anyone have any questions on the math voodoo I just did there, or does that follow for most of you?
Sir, can you please go through that one more time?
Sure. So if I have, I can't make a new page. There we go. So if I have my, well, I can't, my pen is not working. I'm sorry. Hold on a second. Fail me when I need you. Let's try this one more time. Okay. So if I have my probability distribution, and we said our mean was 100, and I wanted to know the probability between 85 and 120, something like this, right? Because I said, what is the probability that X is greater than 85 but less than 120, right? So what I'm really trying to find is the probability of being within this range, right? But my p-norm just finds the probability of being less than a number. So I could say, well, I know the probability of being less than 120 is p-norm of 120, and that's all of that, right? But that's too much because I don't want this area right here, right? I want the stuff that's left over. So what I want is in terms of my functions, I want the probability of X being less than 120. That was all of the green part, but then I need to take off the probability that it is less than 85. And if I do that, that will leave me that part in the middle that I wanted. Does that make sense with that?
Yes, sir. Thank you.
Yeah, and so now I can go into R, and once I've said that is definitely true, then I can just put it in here. P-norm of 120, probability of being less than 120, minus the probability of being less than 85, and I run that, and I get 75, right? 75%. I can look at my picture to say, yeah, that's about right. It was this whole thing to the left minus this part, and this is the range that I am left with, right? Real quick, in the last section, 3 minutes we have here, let's look at Q norm. There is later, if you want to look at, I've got code to look at R norm here. But for Q norm, remember here, I am going to give it a probability, and it's going to give me back an X. So I am saying, what is the X value that I have to be at so that the probability of being less than that X value is 0.65 or 65%. And I can run this, and it tells me here it's 105.7. So already I know that this is not a probability because it's 105. There's no such thing as a probability of 105, right? And if I look at the picture here to kind of give me an idea of what it is, it's saying that blue area is 65%, because that's what I told it. I said, I need it to be 65. And then it found that blue number, 105.8 about, that is the X value that there is a 65% probability of being less than, right? That is what Q norm does. I give it this probability here, 65%, and then it spit back this 105.7798 of saying that is the X value. And I tried to make that clear in my comments of this is what this code is doing. But I highly recommend you guys, if you do download this code, download it, mess around with it, change the numbers, and then see if it reacts the way you thought it did. If it doesn't, then try to figure out why. If not, ask me a question. If you break it and it doesn't work, then just delete it and re-download the fresh file from our server and see what you can do with that. And then if you like it, make your own comments, copy and keep this as part of something so that if I ask you a question like this on the test, you don't have to type it. You can just go, if I say, hey, what's the probability of a standard? You can go in here and say, well, I'm going to change 85 to something else, 120. I'm going to change the mean. I'm going to change the standard deviation. Then you can just run it again, right? So just have that code up there. Okay, we are at time. So you guys are released to go live your USAFA lives and enjoy all of that. I will stick around for a few minutes if anyone has any burning questions. But otherwise, I will see you guys on Wednesday, if not earlier. If you got questions, send them to me. I know I got a queue of questions from the weekend. So as soon as I'm out of here, I'm going to start reading through and responding back to you guys and setting up EI. So I might see some of you guys before Wednesday, but if I don't, I will definitely see you Wednesday morning and give you a hard time about making sure you are turning stuff in that day and doing your quiz. So I will see you on Wednesday, if not before then.
Thank you, sir.
Yep.